Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin our journey through the vastness that surrounds us, take a moment to get comfortable. Let your weight sink into whatever surface holds you. There's nowhere else you need to be. Where in the world are you watching from tonight? A quiet bedroom where the day has finally released its hold? A cozy corner where you've carved out this time for yourself? Wherever you are, you're exactly where you need to be. Tonight we're going to explore something both humbling and strangely comforting. The true scale of our Milky Way galaxy, and just how small Earth really is within it. We'll drift through measurements that stretch the imagination, discover neighbours we didn't know we had, and contemplate what it means to be a tiny blue dot in an ocean of stars. It's a journey that spans 400 billion stars, 100,000 light years, and 13 billion years of history. Along the way, we'll find that our insignificance might be the most beautiful fact about our existence. But don't worry, this isn't going to be an existential crisis wrapped in astronomy. This isn't about feeling lost or alone in an uncaring universe. Instead, we'll move slowly and carefully through the evidence, the scale, the beauty, and the profound connection we have to everything around us. By the end, I think you'll find that being small doesn't mean being meaningless. Sometimes the smallest things contain the most wonder. If you enjoy these calm explorations of our cosmos, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for returning to these slow drifts through space and time. So settle in now, let your shoulders drop away from your ears, feel your jaw unclench, take a slow breath in through your nose and let it out even more slowly. And let's begin our slow drift outward from Earth, through our solar system, past our stellar neighbourhood, and into the spiralling depths of our galactic home. There's nowhere you need to be right now, nothing you need to do. Just listen and let the story unfold. The universe isn't going anywhere. Neither are we. Let's explore it together. Let's begin where we are. Right now, you're on Earth. It feels big, doesn't it? Solid. Substantial. The ground beneath you seems infinite, immovable, the very definition of permanence. But in 1990, as the Voyager 1 spacecraft hurtled toward the edge of our solar system, it turned its camera back toward home one last time. At the request of astronomer Carl Sagan, it captured an image that would change how we see ourselves forever. From 6 billion kilometres away, nearly 4 billion miles, Earth appeared as a single pale blue pixel. Not a marble, not even a dot really, a pixel. One point of light suspended in a sunbeam, barely distinguishable from the cosmic background. If you didn't know where to look, you'd miss it entirely. Everything you know, everyone you've ever heard of, every human who has ever lived out their entire existence on that mote of dust suspended in a sunbeam. Carl Sagan wrote about this image with a kind of reverent wonder. He noted that on that dot, every hunter and forager, every hero and coward, every creator and destroyer of civilizations, every king and peasant, every young couple in love, every hopeful child, every mother and father, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust, suspended, in a sunbeam. The photograph itself is almost painful in its simplicity. The blackness of space dominates. Scattered bands of sunlight streak across the image, artifacts of the camera itself, reminders that we're seeing through technology strained to its absolute limit. And there, in one of those bands so small you have to search for it, is Earth, our whole world. Not even large enough to show continents or oceans, just light. Blue light, pale light, a pixel's worth of reflected sunlight. What makes this image so powerful isn't just the scale, though that's certainly humbling, it's the perspective. For the first time in human history, we could see ourselves from the outside, from a distance so vast that all our divisions became invisible. From 6 billion kilometres, there are no countries, no borders, no religions or races, no rich or poor, just us, all of us, together, on that pale blue dot. And this, remarkably, is just the beginning of understanding our true size. This is Earth from the outer edge of our own solar system, still well within our sun's influence, still gravitationally bound to our star. This is practically next door in cosmic terms. This is Earth from our own neighbourhood, and already we've become nearly invisible. The true scale of our insignificance lies far, far beyond this point, out in the spiral arms of our galaxy, among hundreds of billions of other stars. But we'll get there, slowly, carefully, one comfortable step at a time. For now, just hold that image in your mind. Earth, small and blue and alone, hanging in the darkness. Everything we know, reduced to light. Before we can truly appreciate the scale of our galaxy, we need to understand how astronomers measure these vast distances. Because the numbers involved are so large they lose all meaning, scientists had to invent new units of measurement. New ways of thinking about space itself. Let's start with something familiar. A kilometre is 1,000 metres. It's a distance you can walk in about 10 or 12 minutes at a leisurely pace. You can picture it. You've experienced it. Now imagine 100 kilometres. That's perhaps an hour's drive on a highway. Still comprehensible. Still grounded in human experience. Now imagine 1,000,000 kilometres. That's roughly 2.5 times the distance from Earth to the Moon. Already we're straining at the edges of intuition, but we can still anchor ourselves. It's about how far the Apollo astronauts travelled. But when we step into the realm of interstellar distances, kilometres become absurd. The nearest star to our Sun, Proxima Centauri, is roughly 40 trillion kilometres away. 40 trillion. That's 40 followed by 12 zeros. Our brains simply aren't equipped to comprehend numbers like this. We can write them down, we can calculate with them, but we can't feel them. They're abstract, mathematical, divorced from any lived experience. So astronomers use light years instead. A light year is the distance light travels in 1 year. Light moves at roughly 300,000 kilometres per second, fast enough to circle Earth 7.5 times in a single second. In 1 year, light travels about 9.5 trillion kilometres. That's our new basic unit. And suddenly, cosmic distances become slightly more manageable, at least mathematically. Proxima Centauri isn't 40 trillion kilometres away. It's 4.2 light years away. Still enormous, still incomprehensible in any visceral sense, but at least the number itself fits in our heads. There's something both beautiful and frustrating about this system. Beautiful because it connects distance to time, reminding us that when we look at distant objects in space, we're also looking backward in time. The light from Proxima Centauri that reaches your eye tonight left that star 4 years ago. You're seeing the past. The universe is a time machine by its very nature. But it's frustrating too, because even with this elegant measurement system, the numbers still grow absurdly large. Our galaxy, the Milky Way, is roughly 100,000 light-years across. The nearest major galaxy to ours, Andromeda, is 2.5 million light-years away. Astronomers sometimes use an even larger unit called a parsec, equal to about 3.26 light-years. But for our purposes tonight, light-years will do. What matters isn't the specific unit. What matters is the realization that we're operating on scales so vast that even our measurements are acts of imagination. We're not really measuring in any sense that would be familiar to someone with a ruler or a tape measure. We're calculating, inferring, using the behavior of light itself to triangulate positions in space. And yet, for all these enormous numbers, for all these mind-bending scales, we can still pinpoint Earth's exact location. We know where we are. We've mapped our cosmic address with extraordinary precision. We're on the third planet from a yellow dwarf star, 2/3 of the way out one of the spiral arms of a barred spiral galaxy, in a small cluster of galaxies called the local group. in a larger structure called the Virgo supercluster. We know exactly where we are. We just happen to be in a very, very large universe. And that brings us to the structure we call home, the Milky Way itself, waiting patiently in the darkness beyond our solar system's edge. Our sun feels unique. It's our star, the source of all light and warmth and life on Earth. For most of human history, it was the only star that mattered, the centre of everything. Even after we understood that other stars existed, that they were suns like ours but impossibly distant, our sun retained its special status in our minds. It's the one we orbit, the one we depend on, the one we see every day. But to the Milky Way galaxy, our sun is nothing special. It's one star among somewhere between 200 billion and 400 billion others. The exact count remains uncertain because we can't see all of them. Dust obscures our view. Distance makes the faintest stars invisible even to our best telescopes. But the estimate stands. Hundreds of billions of stars, and ours is just one of them. Think about that number for a moment. 400 billion. If you tried to count to 400 billion, spending 1 second on each number, never sleeping, never pausing, it would take you roughly 12,700 years. That's longer than all of recorded human history. That's longer than agriculture has existed. And each one of those numbers would represent an actual star, a massive ball of nuclear fusion, many of them larger and brighter than our sun, many of them with their own planets, their own systems, their own stories unfolding across billions of years. Our sun is classified as a G-type main sequence star, sometimes called a yellow dwarf, though it's actually more white than yellow when seen from space. It's medium-sized, medium brightness, medium temperature. It's the cosmic equivalent of average. There are stars hundreds of times more massive than our sun, supergiants that would swallow Earth's orbit entirely if placed at our solar system's centre. There are stars barely 1/10 our sun's mass, dim red dwarfs that burn so slowly they'll outlive our sun by trillions of years. There are binary stars, triple star systems, stars being born in nebulae, stars dying in spectacular explosions. The diversity is staggering, and our sun? This unremarkable yellow dwarf sits about 26,000 light-years from the galactic centre. Not in the centre where the action is, where stars cluster densely and a supermassive black hole lurks. Not at the outer edge where stars are sparse and lonely. Right in the middle of the galactic suburbs, in a relatively quiet neighbourhood, in a position that's thoroughly, perfectly average. Even our sun's age is middle of the road. At about 4.6 billion years old, it's roughly 1/3 of the way through its main sequence life. It's not a young star still settling into fusion. It's not an ancient red giant approaching death. It's in the long, stable middle phase, burning hydrogen into helium at a steady, reliable rate. Billions of years to go. Nothing dramatic on the horizon for a very, very long time. From the perspective of galactic geography, our sun's location has probably helped life flourish on Earth. We're far enough from the galactic centre to avoid the intense radiation and gravitational chaos that characterises that region. We're in what astronomers call the galactic habitable zone, a ring-shaped region where conditions are stable enough for planets to form and life to potentially develop. Two orbit in the quiet suburbs. They too orbit in the quiet suburbs. They too enjoy relative stability. They too might harbour worlds where life has found a foothold. Our sun is a single point of light in a galaxy filled with hundreds of billions of other points of light. It's not the brightest, not the largest, not the most interesting to astronomers studying extreme phenomena. It's just ours, and perhaps that's enough. Perhaps being average, being ordinary, being one among billions, is exactly what allowed a small blue planet to develop the conditions necessary for creatures like us to evolve, to wonder, to look up at the night sky and ask where we fit in this vast cosmic tapestry. The Milky Way isn't just a random collection of stars scattered through space. It has structure, architecture, a shape carved by gravity and rotation over billions of years. From our position inside it, We see this structure as a band of light stretching across the night sky, that milky river of stars that gave our galaxy its name. But if we could step outside, if we could view our galaxy from above or below, we'd see something magnificent. A barred spiral galaxy. Its arms sweeping outward from a central bar, stars clustered along these arms like lights on a cosmic highway. Our solar system resides in what's called the Orion Arm, sometimes referred to as the Orion Spur. It's a minor arm, smaller than the galaxy's major arms like Perseus and Sagittarius, but it's home nonetheless. Picture the Milky Way as a grand spiral, arms curving gracefully outward from the centre, and we're in one of the smaller branches between the major arms, about halfway out from the galactic centre to the edge. These spiral arms aren't solid structures. Stars don't stay in the arms permanently, locked in place like lights on a wheel. Instead, the arms are density waves, regions where stars, gas and dust temporarily bunch together as they orbit the galactic centre at different speeds. A star might pass into an arm, spend some millions of years there, then drift out again as it continues its orbit. The arms persist not because the same stars always occupy them, but because stars are constantly flowing through them. Like cars slowing down in highway traffic, our Sun orbits the galactic centre at roughly 250 kilometers per second. That sounds extraordinarily fast, and it is by any earthly standard, but on galactic scales it's a leisurely pace. At this speed, our Sun takes about 230 million years to complete one full orbit around the galaxy. Astronomers call this period a galactic year or cosmic year. In the 4.6 billion years since our Sun formed, it has completed roughly 20 orbits, 20 times around the galaxy, 20 cosmic years. Think about what that means. The last time our solar system was at this exact point in its galactic orbit, dinosaurs walked the Earth. 230 million years ago, the Triassic period was just beginning. Mammals didn't exist yet. Flowering plants hadn't evolved. Earth looked completely different, and yet here we were, cosmically speaking, right here in the Orion Arm, passing through this same general region of space. The spiral arms themselves are regions of intense stellar activity. Stars form in the arms, born from the dense clouds of gas and dust that accumulate there. The brightest, hottest, most massive stars are often found in the arms, because these short-lived giants don't survive long enough to drift out into the space between arms before they explode as supernovae. Our Sun, being older and longer-lived, has had time to move in and out of various arms over its lifetime. From our vantage point within the Orion Arm, we can see portions of the other arms, look toward the constellation Sagittarius, toward the galactic centre. And you're looking through the Sagittarius Arm. Look toward Perseus, and you're seeing the outer Perseus Arm stretching into the distance. The Milky Way's band of light that arcs across our sky is simply our edge-on view of the galactic disk, looking through billions of stars layered one behind the other across thousands of light years. What's remarkable is that we've mapped all this from inside the structure itself. Imagine trying to draw a map of a city while standing at street level, unable to get above the buildings, unable to see more than a few blocks in any direction. That's essentially what astronomers have done with the Milky Way. By measuring distances to stars, tracking their motions, studying the distribution of gas and dust, they've reconstructed our galaxy's shape and determined our place within it. We're in a minor arm, 2/3 of the way out, orbiting steadily through the cosmic suburbs, one small solar system among hundreds of billions drifting through the spiral architecture of our galactic home. Even within our galaxy, even in the relatively crowded spiral arms, space is almost incomprehensibly empty. The distances between stars are so vast that empty barely captures the reality. Let's try to grasp this through scale. Imagine shrinking our solar system down to the size of a coin, a quarter perhaps, about 2.5 centimetres across. At this scale, Pluto's orbit fits within the coin's edge. All the planets, all the asteroid belts, everything gravitationally bound to our Sun, contained in the space of a quarter. Now, at this scale, how far away would the nearest star be? Not across the room, not across a football field. The nearest star, Proxima Centauri, would be roughly 1100 kilometres away. That's about the distance from London to Rome, or from New York to Florida. If our entire solar system fits on a coin, the next solar system is 1,000 kilometres away. That's the emptiness we're dealing with. That's the scale of the void between stars. In actual measurements, Proxima Centauri is 4.2 light-years away. The light you see from that star tonight left its surface 4 years ago. When that light began its journey toward Earth, you were 4 years younger. Different things were happening in your life. The world looked different. And that light just travelled through the void, moving at the fastest possible speed anything can move, taking 4 full years to bridge the gap between there and here. Most of the stars you can see with your naked eye are much farther away than Proxima Centauri. Sirius, the brightest star in Earth's night sky, is 8.6 light-years distant. Betelgeuse, that red supergiant in the constellation Orion, is roughly 550 light-years away. The light from Betelgeuse that reaches your eye tonight left that star in the 1400s, when the Renaissance was just beginning in Europe, when the printing press was being invented, when the world was a fundamentally different place. These distances create profound isolation. Our Sun and its planets occupy a bubble of space approximately 2 light-years across if we count the Oort cloud, that distant shell of icy bodies at our solar system's edge. The next star system begins 4 light-years away. In between is nothing. No planets, no asteroids, no dust or gas in any meaningful quantity. Just emptiness so complete it defies human comprehension. With our current technology, we couldn't reach even the nearest stars within a human lifetime. The Voyager spacecraft, the fastest human-made objects to leave Earth, are travelling at roughly 17 kilometres per second relative to the Sun. At that speed, it would take them about 70,000 years to reach Proxima Centauri, if they were actually headed in that direction, which they're not. 70,000 years. That's roughly the entire span of human behavioural modernity, the entire history of human culture and civilization, all of it not enough time to reach the nearest star. And remember, this is distance within our galaxy, within our own cosmic neighbourhood. We're not talking about reaching other galaxies. We're not even talking about crossing to the other side of the Milky Way. We're just trying to get to the nearest star, the closest point of light beyond our Sun, and it might as well be forever away. This isolation has shaped life on Earth in ways we're only beginning to understand. We evolved in a closed system on a single planet, with no contact with whatever might exist elsewhere. If life exists around other stars, if intelligence has arisen on other worlds, they face the same tyranny of distance. Space itself seems designed to keep neighbours from ever meeting, to ensure that each stellar system remains an island, separated from all others by gulfs that make physical travel across even small galactic distances an almost impossible dream. And yet here we are, aware of all this, mapping our isolation, understanding our position in this vast emptiness, finding meaning perhaps in the very fact that we're trying to comprehend something so much larger than ourselves. That effort itself might be what matters most. Let's pull back now, way back, and try to see our galaxy as a whole. The Milky Way is a disk, flattened by rotation, with a bulge at the centre and spiral arms extending outward. From edge to edge, measuring across the galactic disk, the Milky Way spans roughly 100,000 light-years. In the measurement system we discussed earlier, that's 100,000 times the distance light travels in a year, or roughly 950 trillion kilometres. Numbers like this stop having meaning. Our brains can't hold them. But let's try anyway. Imagine you could travel at the speed of light, the fastest possible speed in the universe. You'd start at one edge of the galaxy, at a star in the outermost spiral arm, and you'd begin crossing toward the other side. At first, stars would be sparse, scattered, lonely points of light in the darkness. But as you dove deeper into the disk, the stars would thicken around you. After 25,000 years of travel, you still wouldn't be halfway across. You'd be approaching the galactic centre, passing through increasingly dense stellar neighbourhoods, dodging gas clouds, witnessing nebulae where new stars are being born. The sky around you would begin to brighten, not with the darkness of interstellar space, but with the combined light of billions of stars. At 50,000 years you'd reach the galactic centre. Here, stars are packed so tightly that planets in this region would have night skies ablaze with thousands of stars bright enough to cast shadows. The supermassive black hole at the very centre, Sagittarius A Star, would be nearby, though you couldn't see it directly. You'd only know it by the way stars orbit impossibly fast around what appears to be nothing, their paths carved by 4 million times our sun's mass compressed into an impossibly small region. And then you'd continue outward, heading toward the far side. Another 50,000 years of travel. The stars would gradually thin out again. You'd pass through the far side spiral arms, watch the stellar density decrease, emerge eventually into the sparse outer edges of the galaxy. 100,000 years of travel at the speed of light, and you'd finally reach the other side. Now remember, you've just travelled faster than anything can actually travel. Light itself took 100,000 years to make this crossing, and in that time, so much would have changed on Earth. 100,000 years ago, modern humans were just beginning to migrate out of Africa. We were hunter-gatherers. We had fire, stone tools, language probably, but nothing we'd recognise as civilization. Agriculture was 90,000 years in the future. Writing was 95,000 years away. The pyramids wouldn't be built for another 97,000 years. The light from the far edge of our galaxy that reaches Earth tonight began its journey before we were fully human in any sense we'd recognise today. That light has been travelling through space longer than we've had art, longer than we've buried our dead with ceremony, longer than we've wondered about the stars themselves. It set out on its journey in a universe that had no humans to observe it, and it arrives tonight in a universe where humans have built telescopes powerful enough to catch it, to analyse it, to understand what it tells us about the distant reaches of our galactic home. This is the scale we're operating on. This is the size of just our galaxy, not the universe, not even our local group of galaxies, just our single galaxy, the Milky Way. 100,000 light-years across, home to hundreds of billions of stars, and somewhere in there, about 2/3 of the way out from the centre, is our sun, our solar system, our Earth. One tiny world, one pale blue dot, getting smaller by the moment as we pull back and see the full scope of the structure we call home. The Milky Way isn't just wide, it's also relatively thin, at least in cosmic terms. While the galactic disk stretches 100,000 light-years from edge to edge, its thickness is only about 1,000 light-years for most of the disk, with a thicker bulge of about 10,000 light-years at the galactic centre. Imagine a dinner plate. Now imagine that same plate scaled up to the width of a major city. That's roughly the proportions we're talking about. Our galaxy is a vast flat disk of stars spinning through the void. Most of the galaxy's stars, including our Sun, orbit within this relatively thin disk. But some stars have more eccentric orbits, carrying them above or below the galactic plane. These stars, often older population stars that formed in the galaxy's early history, swing up out of the disk and then back down through it in long lazy arcs. They're the exception though. The majority of the Milky Way's mass, the vast majority of its stars and gas and dust, concentrate in that flat disk, bound there by gravity and angular momentum. If you could somehow travel perpendicular to the galactic disk heading straight up from our position, you'd leave the busy stellar neighbourhood relatively quickly. Within a few hundred light-years, the stars would thin out dramatically. Within 1,000 light-years, you'd be above the main disk, looking down on the spiral structure from a vantage point we can only simulate with computers. and careful astronomical mapping. Above the disk, you'd find yourself in what's called the galactic halo, a roughly spherical region surrounding the disk where globular clusters orbit. These clusters are ancient, dense spheres of stars, some containing hundreds of thousands of stars packed into regions just dozens of light years across. They're among the oldest objects in the galaxy, nearly as old as the galaxy itself, fossils from the Milky Way's youth when it was still forming from smaller proto-galaxies merging together. The space above and below the galactic disk contains very little ordinary matter. It's emptier than the already empty space between stars in the disk, but it's not empty of everything. Dark matter, that mysterious substance that doesn't emit or absorb light but makes its presence known through gravity, extends far beyond the visible disk, creating a massive dark matter halo that dwarfs the visible galaxy. We can't see this halo directly, but we know it's there because the galaxy's rotation doesn't make sense otherwise. The outer stars orbit too fast. Without dark matter's additional gravity holding them in, they should fly apart. But they don't. Before we continue, I want to pause for just a moment. Because what you have learned in the last 30 minutes is something genuinely rare. Most people move through their entire lives without ever stopping to understand the world at this level. But you did. Tonight you chose curiosity over noise and depth over distraction. That is exactly who this channel was made for. If you want to keep being that person, a like and subscribe takes 2 seconds and make sure this channel never stops finding you. Now, let's go deeper. But they don't. Something invisible, something that outweighs all the stars and gas and dust combined, holds the galaxy together. Looking down from above the galactic plane, you'd see the spiral structure clearly. You'd see the central bar, that elongated concentration of stars at the galactic core, with spiral arms trailing off from its ends. You'd see how the arms aren't solid, but rather composed of countless individual stars, each following its own orbit, temporarily bunching together in patterns that create the illusion of structure. It would look, perhaps, like a hurricane seen from space, that same spiral beauty, that same sense of motion frozen in a photograph that's actually capturing something deeply dynamic. But you'd also see how small Earth is from this vantage point. Even from just a few thousand light years above the galactic plane, even from what's practically no distance at all on galactic scales, our solar system would be invisible. You couldn't pick it out. You couldn't find our sun among the billions of other stars. We'd be hidden in the crowd, lost in the overwhelming glitter of the galactic disk. And if you travelled far enough away, tens of thousands of light years above the disk, the entire galaxy would become a single object in your view. Not individual stars anymore, just light. A pinwheel of light. Beautiful and vast and entirely indifferent to anything happening on its surface. Somewhere in that light would be Earth. Somewhere in that glow would be every human who has ever lived. But you wouldn't be able to see us. You wouldn't even be able to see our star. We'd be less than pixels at that distance. We'd be statistical probabilities, rounding errors in the census of galactic matter, and that would still be just within our own galaxy, not even beginning to approach the distances between galaxies, the voids that make our cosmic loneliness even more profound. 4 million suns compressed to nothing. At the very centre of our galaxy, lurking in the constellation Sagittarius as seen from Earth, is something both fascinating and deeply strange. A supermassive black hole called Sagittarius A Star, pronounced __quote_1__. It contains the mass of approximately 4 million suns, all compressed into a region smaller than Mercury's orbit around our Sun. It's the gravitational anchor of our entire galaxy, the point around which hundreds of billions of stars orbit, including our own. For a long time, astronomers suspected something massive must be at the galactic centre, but they couldn't see it directly. Dust obscures our view of the galactic core in visible light. But in the 1990s and 2000s, astronomers using infrared telescopes which can see through dust began tracking the orbits of stars very close to the galactic centre. They watched these stars move, plotting their positions year after year, and what they discovered was extraordinary. Some of these stars orbit Sagittarius A Star so closely and so quickly that they complete an entire orbit in just a few years. A star called S2, for example, orbits the black hole every 16 years at speeds reaching nearly 5% the speed of light at its closest approach. That's roughly 15 million kilometers per hour. Nothing but an immense gravitational field could cause a star to move that fast. By carefully measuring these stellar orbits, astronomers calculated the mass of whatever they were orbiting, and the number they arrived at was staggering: 4 million times the Sun's mass. But here's the remarkable part. Despite this enormous mass, Sagittarius A Star itself is relatively small. The event horizon, the boundary beyond which nothing can escape, is only about 12 million kilometers in radius, or roughly 17 times the radius of our Sun. 4 million suns worth of mass compressed into a volume you could fit comfortably inside Mercury's orbit. The density is incomprehensible. The gravitational field is so strong that space itself bends dramatically around it. This black hole doesn't pull stars in like some cosmic vacuum cleaner, though. That's a common misconception. The stars orbiting it are in stable orbits, just like planets orbit the Sun. They're not spiralling inward. They're not being dragged to their doom, at least not on timescales relevant to human observation. They orbit predictably and reliably, held in balance by their orbital velocity and the black hole's gravity. Every so often, though, something does fall in. A gas cloud might drift too close, getting pulled apart by tidal forces and stretched into a stream of superheated material that spirals into the black hole, glowing brilliantly in X-rays as it heats up from friction and compression. Astronomers have watched this happen, observing clouds and even stars get tidally disrupted and consumed. It's violent on scales difficult to imagine, but it's also relatively rare. Most of the time, Sagittarius A Star is quiet, almost dormant, just sitting there at the galaxy's heart, holding everything in orbit around it. We're safe from it, though. 26,000 light-years away, our solar system feels essentially no direct gravitational influence from the supermassive black hole. We orbit the galactic centre as a whole, responding to the combined mass of billions of stars and vast amounts of dark matter, not to the black hole specifically. It's just one component of the galactic mass distribution, albeit a fascinating one. In 2022, astronomers released the first image of Sagittarius A Star itself, or rather the glowing ring of matter around it. Using a network of radio telescopes scattered around Earth, working together as a single planet-sized telescope, they captured the shadow of the event horizon surrounded by a bright ring of superheated gas. It was a triumph of observational astronomy, proof that we could image the very centre of our own galaxy, could peer through 26,000 light-years of intervening space and dust and see the darkness at the heart of our cosmic home. That darkness, that central black hole, has been there for most of the galaxy's history. It grew as the galaxy grew, fed by material falling in over billions of years. It will be there long after our sun dies, long after Earth is gone. It's the most permanent structure in our galaxy, a gravitational well so deep that not even time escapes it unchanged. And yet, for all its mass and mystery, it's just one feature among many in this vast spiral of stars we call the Milky Way. One darkness among countless lights, one anchor point in a galaxy filled with hundreds of billions of other fascinating, beautiful, complex stellar systems. The Milky Way isn't just old stars slowly burning out. It's also actively creating new stars, forging fresh suns from clouds of gas and dust in regions called stellar nurseries. These nebulae, vast clouds of hydrogen and helium mixed with heavier elements from previous generations of stars, are where the next chapter of the galaxy's story is being written. Take the Orion Nebula, one of the most studied stellar nurseries in our galactic neighbourhood. It's about 1,300 light-years from Earth, close enough that we can observe it in extraordinary detail. The nebula spans roughly 24 light-years across, and within its glowing gas clouds thousands of new stars are being born. Some have already ignited fusion, others are still protostars, contracting under their own gravity, not yet hot enough at their cores to begin burning hydrogen into helium. The process of star formation is both simple in principle and extraordinarily complex in detail. It begins with a dense region in a molecular cloud where gas has accumulated. Perhaps a nearby supernova explosion sent a shockwave through space, compressing the gas. Perhaps two clouds collided. Perhaps the gas simply reached a critical density on its own. Whatever the trigger, gravity takes over. The cloud begins to collapse. As it collapses, it heats up. Conservation of angular momentum causes it to spin faster, flattening into a disk. At the centre, a protostar forms, growing denser and hotter as more material falls in. Eventually, if the protostar accumulates enough mass, the temperature and pressure at its core reach the threshold for nuclear fusion. Hydrogen atoms begin fusing into helium. Energy radiates outward. The protostar becomes a star. A new point of light in the galaxy. But the process doesn't end cleanly. The new star's radiation and stellar wind blow away the remaining gas and dust. Sometimes this creates beautiful structures like the pillars of creation in the Eagle Nebula, towering columns of gas where star formation is still ongoing at the tips, protected somewhat from the harsh radiation of nearby massive stars. Sometimes it simply clears the area, revealing a young star cluster where hundreds or thousands of stars form together from the same parent cloud. Our own Sun formed this way. 4.6 billion years ago, in a now dispersed stellar nursery. We know this because the planets in our solar system contain elements heavier than hydrogen and helium, elements that could only have been created in previous generations of stars and then scattered into space when those stars exploded as supernovae. Our Sun is at least a second-generation star, possibly third or fourth. It formed from a cloud enriched by the death of earlier stars, inheriting their heavy elements, using them to build rocky planets and eventually life. The Milky Way creates roughly 7 new stars every year on average. That might not sound like much, but over billions of years it adds up. Most of these new stars are small, dim red dwarfs that will burn slowly for trillions of years. Some are medium stars like our Sun. A few are massive blue giants that will burn bright and die young, exploding as supernovae within just a few million years and enriching the interstellar medium with heavy elements, seeding the next generation of star formation. These stellar nurseries are concentrated in the spiral arms, where gas and dust accumulate due to the density waves we discussed earlier. That's why the spiral arms look bright and blue in photographs of other galaxies. They're filled with young, hot, massive stars that shine brilliantly in ultraviolet and blue light. Meanwhile, the spaces between the arms tend to look yellower and dimmer, populated by older, cooler stars that have had time to drift away from their birthplaces. Looking at these nurseries, at these places where stars are born, reminds us that the galaxy is not static. It's dynamic, alive in its own way. It creates, it destroys, it recycles matter through generations of stellar life and death. The atoms in your body were forged in stars that died before our Sun was born. Those atoms were scattered into space, incorporated into the molecular cloud that collapsed to form our solar system, gathered into Earth, and eventually arranged into the complex patterns we call life. You are made of stardust, literally, and the process that made you is still ongoing in stellar nurseries throughout our galaxy, creating new stars, new planets, new possibilities for the universe to know itself. For all the stars, for all the nebulae and clusters and stellar nurseries, most of our galaxy is empty space. Even in the densest regions of the spiral arms, even near the galactic centre where stars cluster more tightly, the distances between stars remain vast, and the space between those stars remains profoundly, almost perfectly empty. Let's think about this carefully. We've established that the Milky Way contains somewhere between 200 and 400 billion stars. That sounds like an incomprehensibly large number, and it is. But it's distributed across a volume roughly 100,000 light-years wide and 1,000 light-years thick at the disk. The math works out to a stellar density of about 0.04 stars per cubic light-year in the galactic disk, and that's in the relatively crowded regions. In the spaces between spiral arms, the density drops even further. What does this mean in practical terms? It means if you were standing on a planet around a star between the spiral arms, your night sky would be noticeably darker than ours. Fewer bright stars, more darkness. The Milky Way band across your sky would still be visible, but it would be dimmer, less impressive, a reminder that you lived in one of the galaxy's quieter neighbourhoods, away from the stellar traffic of the spiral arms. These regions between the arms are called inter-arm regions, and they contain older stellar populations, stars that formed in spiral arms long ago and have since drifted out into the calmer spaces. They're still orbiting the galactic centre. They're still moving at hundreds of kilometres per second, but they're no longer part of the dense concentrations that define the spiral structure. The emptiness extends in all directions. Look up from the galactic plane, toward the galactic poles, and you'd find even less. The stars thin out dramatically. The bright disk becomes a distant glow. You'd enter the realm of the galactic halo, that roughly spherical region surrounding the disk where only globular clusters and ancient population 2 stars orbit in their long, slow paths around the galactic centre. It's worth sitting with this emptiness for a moment, really trying to feel it. Space is not the crowded place science fiction often portrays. There are no asteroid fields you'd have to carefully navigate. There are no densely packed stars constantly threatening collision. The reality is almost the opposite. Space is so empty that if you chose a random point within our galaxy and placed yourself there, the odds are overwhelming that the nearest star would be light years away, an unreachable point of light in an ocean of darkness. This emptiness has practical consequences. It means we're isolated, as we discussed earlier. It means other civilizations, if they exist, are likely similarly isolated. It means the galaxy is filled with lonely islands of matter, separated by voids so vast that bridging them seems almost impossible. But the emptiness also means something else, something perhaps more profound. It means the universe has room for countless stellar systems to evolve in peace, without interference, without disruption. Room for planets to form and settle into stable orbits. Room for chemistry to become biology. Room for life to experiment with different forms across billions of years. The emptiness isn't absence, it's possibility. It's the space where things can happen without being constantly disturbed by neighbouring systems. Earth's isolation might be one of the factors that allowed life to flourish here. We're far enough from other stars that we don't experience disruptive gravitational influences. We're far enough from the galactic centre to avoid intense radiation. We're far enough between things to be safe, yet close enough to other stars to have a beautiful night sky that inspired our ancestors to wonder, to question, to eventually develop astronomy and begin understanding our place in the cosmos. The voids between the spiral arms are dark and empty and vast, but they're also part of what makes the galaxy work, part of what allows it to be simultaneously crowded with stars and filled with space, simultaneously full and empty, simultaneously home to billions of stellar systems and yet profoundly, beautifully alone. And this brings us to an interesting question, one worth contemplating as we move deeper into our journey. What does it mean to be insignificant in a place this vast? Is smallness the same as meaninglessness? Or is there something else going on here? Something more subtle and more beautiful than simple cosmic irrelevance? Let's return to something we touched on earlier and explore it more deeply. Our nearest stellar neighbour, the Alpha Centauri system. At 4.37 light-years from our solar system, it's the closest star system to Earth, and yet that closeness is still unimaginably vast. This system offers a perfect case study in cosmic distances, in what nearby actually means on galactic scales. Alpha Centauri isn't a single star, it's a triple star system. The two main stars, Alpha Centauri A and Alpha Centauri B, orbit each other in an elegant gravitational dance, completing an orbit every 80 years or so. They're similar to our Sun in many ways. Alpha Centauri A is slightly larger and brighter. Alpha Centauri B is slightly smaller and dimmer. Together they form a binary pair that would be spectacular to observe from nearby planets. The third component, Proxima Centauri, is a small red dwarf star that orbits the AB pair at a distance of about 13,000 astronomical units. That's 13,000 times the distance from Earth to the Sun. Far enough that Proxima's orbit around the other two stars takes hundreds of thousands of years. It's barely bound to the system, held there by the weakest gravitational threads, and might eventually escape into interstellar space on its own. Proxima Centauri is the closest of the three to our solar system, and it's received a lot of attention in recent years because astronomers have discovered planets orbiting it. At least one planet, Proxima Centauri B, orbits in what might be the habitable zone, the region where liquid water could potentially exist on a planet's surface. This has sparked speculation about whether life might exist there, whether we might someday send probes to investigate, whether humanity's first contact with another world biology might happen around our nearest stellar neighbour. But the reality of the distance remains sobering, 4.37 light-years. If we sent a probe using our current fastest technology, it would take tens of thousands of years to arrive. Even if we developed propulsion systems significantly better than what we have now, even if we achieved speeds of, say, 10% the speed of light through some yet-to-be-invented technology, the journey would still take over 40 years. A human crew would age and die en route unless we developed either suspended animation or generation ships designed to support multiple generations of crew members. And this is the closest star system. This is our next-door neighbour in cosmic terms. Everywhere else is even farther away. The second nearest star system, Barnard's star, is 6 light-years distant. Sirius, so bright in our night sky that ancient Egyptians based their calendar on its movements, is 8.6 light-years away. Wolf 359 is 7.9 light-years away. Lalande 2185 is 8.3 light-years away. The names become catalogue numbers, the distances grow, and nowhere is actually reachable with current technology. From a world orbiting Alpha Centauri, our Sun would appear as a bright star in their sky, visible in the constellation Cassiopeia from their perspective. Observers there could study our Sun with their telescopes, analyse its light, determine its composition, even detect the gravitational wobbles caused by Jupiter's mass tugging on our Sun as it orbits. They could know we exist. They could know our Sun has planets. But visiting would be just as impossible for them as it is for us. This mutual isolation creates an interesting philosophical situation. If intelligence has evolved around Alpha Centauri, if creatures have developed technology and looked up at the stars and wondered if they were alone, they face the same barriers we do. 4 light-years might as well be 4 million years given the practical difficulties of crossing it. We could exchange radio signals, perhaps. Lightspeed communication would have a round-trip delay of about 9 years. 4 years for our message to reach them, 4 years for their reply to reach us, plus however long they take to compose a response. A conversation would be measured in decades, each question and answer pair requiring nearly a decade to complete. The Alpha Centauri system reminds us that the galaxy is full of neighbours we'll probably never meet, worlds that might harbour life or intelligence or wonders we can barely imagine. All of them separated from us by distances that make contact extraordinarily difficult, if not impossible. The galaxy is simultaneously full and empty, crowded with stars yet profoundly lonely, each system an island unto itself, capable of detecting others but rarely if ever capable of reaching them. And Alpha Centauri, our nearest neighbour, the closest other star system in the entire galaxy, perfectly embodies this paradox. Close enough to study, close enough to see, close enough to dream about, and yet so far away it might as well be unreachable forever. Our solar system doesn't just orbit through the galaxy in isolation. We're actually inside a structure called the local bubble, a roughly spherical cavity in the interstellar medium about 1,000 light-years across. This bubble is a region where the gas and dust between stars is thinner than average, heated and cleared out by ancient supernova explosions that occurred millions of years ago. The interstellar medium, the gas and dust that fills the space between stars, isn't uniform. It's clumpy, structured, shaped by stellar winds and supernova explosions and the general dynamics of the galaxy. In some regions, it's dense enough to collapse and form new stars. In other regions, like the local bubble, it's been blown clear, leaving a cavity of hot, thin gas. Scientists think the local bubble formed somewhere between 10 and 20 million years ago, when multiple massive stars in our region of the galaxy reached the end of their lives and exploded as supernovae. These explosions released enormous amounts of energy, heating the surrounding gas to millions of degrees and pushing it outward, creating an expanding bubble of hot, low-density material. Over millions of years, this bubble grew, and our solar system happened to be close enough to drift into it. Inside the local bubble, the density of hydrogen gas is about 0.05 atoms per cubic centimetre, compared to about 0.5 atoms per cubic centimetre in the surrounding interstellar medium. That might not sound like much of a difference, but in space, where distances are vast and even small differences in density accumulate over light years, it's significant. The local bubble is genuinely less dense, genuinely clearer, a hollow in the galactic medium. The walls of the bubble, where the hot interior gas meets the denser surrounding medium, are regions of active star formation. The compression at the boundaries has triggered the collapse of molecular clouds, creating new stellar nurseries. Some of the bright young stars and nebulae we see in our night sky, like those in the Scorpius-Centaurus association, are actually in the walls of the local bubble, born from the very shock waves that created the cavity we now inhabit. Our solar system entered the local bubble sometime in the last few million years, and will remain inside it for several more million years before our orbit around the galaxy carries us out the other side. In cosmic terms, we're just passing through, temporarily enjoying clearer skies, lower interstellar gas density, and slightly less cosmic ray flux than we'd experience in denser regions of the interstellar medium. This has consequences for Earth, though subtle ones. The interstellar medium affects the heliosphere, that bubble of solar wind our sun creates around the solar system. It affects the cosmic ray environment, which in turn affects Earth's atmosphere and climate in ways we're still trying to fully understand. Being inside the local bubble means we're experiencing slightly different cosmic conditions than we would in a denser region of space. Mapping the local bubble has been a major achievement of modern astronomy. By measuring distances to nearby stars, tracking the distribution of interstellar gas, and studying the motions of stellar associations, astronomers have reconstructed the three-dimensional structure of our local region of space. They've identified the bubble's boundaries, located the stellar associations in its walls, and traced the likely history of the supernova explosions that created it. What's fascinating is that this structure, this cavity we're passing through, is itself quite small on galactic scales. 1,000 light-years across sounds vast, and it is vast. But remember, the Milky Way is 100,000 light-years across. The local bubble is just 1% of the galactic diameter. It's a tiny local feature, a minor structure in one small region of one spiral arm of our galaxy. And yet it's home. It's where we are right now at this moment in cosmic history. Our solar system drifts through this cleared region of space, enjoying slightly better visibility to distant stars, slightly less interference from interstellar dust, all because millions of years ago some massive stars will never know the names of exploded and created this bubble of hot, thin gas that we now call our local neighbourhood. Even our immediate cosmic environment, even the space right around our solar system, is shaped by forces larger than ourselves. by events that happened long before Earth existed in its current form, by the deaths of stars we never saw but whose legacy we live inside. Not everything in the galaxy orbits a star. Astronomers have discovered, to their surprise, that there are likely billions of rogue planets wandering through the Milky Way, worlds that either formed in isolation or were ejected from their home star systems through gravitational interactions. Now, drifting alone through interstellar space with no sun to warm them, no star to orbit, no stellar anchor to call home. These rogue planets are difficult to detect precisely because they don't orbit stars. We typically find exoplanets by watching for the slight dimming of a star as a planet passes in front of it, or by measuring the slight wobble in a star's position caused by an orbiting planet's gravity. But rogue planets have no star to betray their presence. They're dark, cold, invisible objects drifting through the darkness, only occasionally revealing themselves when they pass in front of a more distant star, and their gravity bends that star's light in a detectable way through a process called gravitational microlensing. How do planets become rogues? The most common scenario probably involves young star systems, where multiple planets are still settling into their final orbits. Gravitational interactions can be chaotic in these early stages. Planets can gravitationally scatter each other. In some cases, one planet gets flung outward, gaining enough velocity to escape the star's gravity entirely, while another planet settles into a tighter, more stable orbit. The ejected planet becomes a rogue, destined to wander the galaxy indefinitely. Another possibility involves binary star systems or star clusters, where close encounters between stars can disrupt planetary systems, flinging planets out into interstellar space, or perhaps some rogue planets formed in isolation, condensing from gas clouds that weren't quite massive enough to become stars, never belonging to any stellar system at all. Whatever their origins, these worlds are profoundly alone. They receive no warmth from a sun. Their surfaces, if they have solid surfaces, are frozen, dark, far colder than anywhere in our solar system. Any atmosphere they once had might have frozen out, condensed into ice on their surfaces, or lost to space entirely. They drift through the galaxy at tens or hundreds of kilometers per second, following their own lonely orbits around the galactic centre, solitary worlds among the stars. Current estimates suggest there might be as many or more rogue planets than there are stars in the galaxy. That's a staggering thought. For every star you see in the night sky, there might be one or more planets drifting unseen in the darkness between. The galaxy might be filled with these orphaned worlds, creating a hidden population of planets that outnumbers the planets orbiting stars. And yet some of these rogue planets might not be completely dead. If a planet is massive enough, it could retain internal heat from its formation, radioactive decay, and tidal heating if it has moons. This internal heat could potentially maintain subsurface oceans beneath thick icy shells, similar to what we see on Jupiter's moon Europa or Saturn's moon Enceladus. In theory, such oceans could provide habitable environments even in the absence of sunlight, supporting life through chemosynthesis rather than photosynthesis. It's a strange and somewhat haunting thought. Worlds drifting in total darkness, perhaps harbouring life in their hidden oceans. Existing in a completely different mode than life on Earth, never seeing stars, never experiencing seasons or day-night cycles, existing in a timeless, lightless, eternal now beneath kilometres of ice, warmed only by the dying heat of the planet's core. These rogue planets challenge our assumptions about what planetary systems look like, about what counts as a habitable world, about the diversity of environments that might exist throughout the galaxy. They remind us that the universe is stranger and more varied than our Earth-centric intuitions would suggest. Not everything orbits a star. Not everything follows the patterns we see in our own solar system. The galaxy contains multitudes, and among those multitudes are countless worlds wandering alone. Dark and cold and possibly alive with strange life we can barely imagine. The existence of rogue planets also adds another dimension to our cosmic insignificance. Not only is Earth a small world orbiting an average star in the suburbs of a large galaxy, but we're also lucky enough to have a star at all. We're lucky to receive warmth and light. We're lucky to be anchored to something, to have a sun that defines our days and our years. Billions of worlds don't have that. They drift in darkness, and by comparison, our situation suddenly seems less bleak, more fortunate, a cosmic blessing we too often take for granted. The Milky Way hasn't always been the size it is today. Like most large galaxies, it has grown over billions of years by consuming smaller galaxies, a process astronomers call galactic cannibalism. The evidence for this lies in stellar streams, long trails of stars that wrap around our galaxy, the scattered remains of smaller galaxies that came too close and were torn apart by the Milky Way's gravity. One of the most famous of these streams is the Sagittarius dwarf elliptical galaxy, or Sagittarius stream for short. This small galaxy is currently being pulled apart by the Milky Way's tidal forces. It orbits our galaxy in a polar orbit, passing up and over the galactic disk and then down below it. With each pass, the Milky Way's gravity stretches it, pulling stars from its edges, creating a stream of stars that wraps around the entire galaxy multiple times. Astronomers discovered the Sagittarius stream by mapping the positions and velocities of stars in our galactic halo, and noticing that some stars move together in coherent groups, all following similar paths through space. These groups turned out to be the remnants of the Sagittarius dwarf, stars that used to belong to a distinct galaxy, but are now being assimilated into the Milky Way's halo population. The process takes hundreds of millions of years. The Sagittarius dwarf has probably orbited the Milky Way many times, each orbit stripping away more stars, gradually reducing its mass until eventually nothing will be left but a dispersed stream of stars, their common origin erased by time and tidal forces. In the far future, astronomers in the Milky Way might not even recognise these stars as coming from a separate galaxy. They'll just be part of the halo, ancient stars with unusual compositions, hints of a history that's been mostly forgotten. This isn't an unusual process. Large galaxies grow this way, accumulating mass by consuming smaller neighbours. The Milky Way has likely absorbed dozens of small galaxies over its history. Each one leaves a trace, a stellar stream, or an unusual stellar population in the halo, a ghost of what it once was. These streams are fossil records, evidence of the Milky Way's violent past, proof that our galaxy's history involves collision and merger, and the gradual consumption of everything nearby that couldn't escape our gravity. The Magellanic Clouds, two irregular dwarf galaxies visible from the southern hemisphere, are also likely to be consumed by the Milky Way eventually. They orbit our galaxy, and while they've so far avoided being torn apart, simulations suggest that in a few billion years they'll spiral inward and merge with us. Continues throughout the universe. Large continues throughout the universe. Large galaxies consume small galaxies. Medium galaxies merge with each other to form larger galaxies. The cosmic story is one of growth through merger, of complexity arising from simpler components coming together under gravity's inexorable pull. But the mergers aren't always gentle. When two galaxies collide, their stars rarely actually hit each other. Space is too empty for stellar collisions to be common, but the gas clouds do collide, compressing and triggering enormous bursts of star formation. The galactic structures get disrupted, twisted into new shapes by gravitational interactions. Supermassive black holes at the centres of the merging galaxies eventually spiral together and merge in catastrophic events that send gravitational waves rippling across the universe. The Milky Way itself is on a collision course with the Andromeda galaxy, our nearest large galactic neighbour. In about 4 to 5 billion years, these two galaxies will collide and merge, creating a new, larger elliptical galaxy that astronomers have playfully dubbed Andromeda. By that time, our Sun will be nearing the end of its life anyway, possibly already in its red giant phase. Earth might not survive the sun's expansion, but even if it does, the view of the night sky will be dramatically different during the merger, filled with the combined stars of two galaxies gradually mixing together. Galactic cannibalism reminds us that even galaxies aren't permanent structures. They grow, change, merge, and evolve over billions of years. The Milky Way today is different from the Milky Way of 10 billion years ago, and will be different from the Milky Way of 10 billion years hence. We exist at one moment in this galaxy's long history, living on a planet orbiting a star in a galaxy that's slowly consuming its neighbours and heading toward an eventual merger with Andromeda. Even on scales where we might think things are stable and eternal, change is the only constant. Everything we've discussed so far, all the stars and planets and gas and dust and black holes, all of it together makes up only about 15 to 20% of the Milky Way's total mass. The rest, the vast majority of what holds our galaxy together, is dark matter, a form of matter that doesn't emit, absorb or reflect light, making it completely invisible to telescopes, detectable only through its gravitational effects. This sounds almost like science fiction, like something invented to patch holes in our understanding. But the evidence for dark matter is overwhelming and comes from multiple independent sources. The first hint came in the 1930s when astronomer Fritz Zwicky studied the motions of galaxies in the Coma cluster and realised they were moving too fast. The visible matter in the cluster wasn't enough to gravitationally hold the cluster together at those speeds. Something invisible, something dark, had to be providing additional gravity. In the 1970s, astronomer Vera Rubin made similar observations studying the rotation curves of spiral galaxies, including the Milky Way. She found that stars in the outer edges of galaxies orbit just as fast as stars closer to the galactic centre, which doesn't make sense if only the visible matter is providing gravity. According to basic physics, stars farther from the galactic centre should orbit more slowly, just like outer planets in our solar system orbit the Sun more slowly than inner planets. But they don't. They orbit at roughly the same speed all the way out to the visible edge of the galaxy. The only explanation that makes sense is that galaxies are embedded in massive halos of dark matter that extend far beyond the visible disk. This dark matter provides the additional gravity needed to keep the outer stars moving at their observed speeds. Without it, galaxies should fly apart. The stars should escape into intergalactic space, but they don't, because dark matter holds them in. We don't know what dark matter is made of. It's not ordinary matter, not protons and neutrons and electrons. If it were, it would interact with light, and we'd be able to see it. The leading theory is that dark matter consists of particles that interact only through gravity and possibly the weak nuclear force, making them extraordinarily difficult to detect. Physicists have built incredibly sensitive detectors deep underground, shielded from cosmic rays and background radiation, trying to catch a dark matter particle interacting with ordinary matter. So far, these experiments have found nothing conclusive, but the search continues. What we do know is that dark matter is everywhere. It's in our galaxy, creating a roughly spherical halo that extends well beyond the visible disk. It's in galaxy clusters, providing the gravity that holds thousands of galaxies together. It's in the cosmic web, the large-scale structure of the universe, where dark matter filaments connect galaxy clusters across hundreds of millions of light-years. It's in the space around our solar system, possibly even passing through your body right now, trillions of dark matter particles streaming through you every second without interacting, ghosting through matter as if it weren't there. The amount of dark matter is staggering. Current estimates suggest dark matter outweighs ordinary matter by about 5 to 1. For every kilogram of atoms, there are approximately 5 kilograms of dark matter. The universe is mostly made of stuff we can't see, can't touch, can't detect except through its gravitational influence. Everything we've ever seen with telescopes, every star and galaxy and nebula, is the minority component of the universe. The majority remains hidden, dark, mysterious. This realization adds yet another layer to our cosmic insignificance. Not only are we on a small planet orbiting an average star in the suburbs of a large galaxy, not only is our galaxy one of hundreds of billions in the observable universe, but even the matter we're made of, the atoms that constitute everything we can see and touch, is the rare stuff, the unusual matter, the minority component. Most of the universe is made of something completely different, something we don't understand, something that doesn't care about light or chemistry or life. And yet, paradoxically, we owe our existence to dark matter. Without it, galaxies wouldn't have formed properly in the early universe. The dark matter collapsed first, creating gravitational wells that allowed ordinary matter to fall in and accumulate into dense regions that eventually became stars and galaxies. Dark matter provided the scaffolding, the invisible framework around which the visible universe assembled itself. Visible beauty, for all its hundreds of visible beauty, for all its hundreds of billions of stars, is really a dark matter halo with a bright core. The stars are the decoration. The dark matter is the structure. We see the lights but miss the architecture, see the surface but not the depths. And perhaps that's fitting. Perhaps it's appropriate that even as we map our galaxy, even as we measure its scale and understand our insignificance within it, there remains something fundamentally mysterious about it, something beyond our current ability to fully grasp, a reminder that the universe is larger and stranger than even our most comprehensive theories suggest. The Milky Way is old. Not quite as old as the universe itself, which is approximately 13.8 billion years old, but close. Current evidence suggests our galaxy began forming about 13 billion years ago, in the early universe when the first generation of stars was just ending, and the first galaxies were beginning to assemble from smaller proto-galaxies. In those early times, the universe looked very different. There were no spiral galaxies yet. No grand spirals with beautiful arms sweeping through space. Instead, there were small, irregular galaxies, clumps of stars and gas gathered together by dark matter halos, colliding and merging in a chaotic dance driven by gravity. The Milky Way formed through this process of hierarchical assembly, small galaxies merging to form larger ones, those merging to form larger still, eventually creating the massive spiral we see today. The oldest stars in our galaxy, found mostly in globular clusters in the galactic halo, are nearly as old as the universe itself, some approaching 13 billion years in age. These ancient stars formed from primordial gas that consisted almost entirely of hydrogen and helium, the elements created in the Big Bang. They contain almost no heavy elements, no carbon or oxygen or iron, because those elements didn't exist yet. They would be created later, inside stars, and scattered into space by supernovae. As generations of stars lived and died, they enriched the interstellar medium with heavy elements. Each supernova explosion scattered atoms of carbon, nitrogen, oxygen, silicon, iron, and dozens of other elements into space. These atoms mixed with the primordial hydrogen and helium, creating increasingly chemically complex gas clouds. Later generations of stars formed from this enriched gas, and these stars, including our Sun, contain much higher percentages of heavy elements than the ancient first-generation stars. This process continues today. Stars are still being born in nebulae throughout the galaxy. They're still enriching the interstellar medium when they die. The Milky Way is still evolving, still changing, still writing its chemical history one stellar generation at a time. We are living in the middle chapters of this story, not the beginning and not the end. The galaxy's structure has changed over time too. The Milky Way probably wasn't always a barred spiral. It might have been a more irregular shape in its youth, only settling into its current spiral structure a few billion years ago, as rotation and density waves organised the stellar distribution into the patterns we see today. The central bar might be a relatively recent feature formed within the last few billion years through gravitational instabilities in the galactic disk. Looking forward, the Milky Way will continue to change. we're still consuming smaller satellite galaxies. We're still heading toward our eventual collision with Andromeda in 4 to 5 billion years. When that merger happens, the Milky Way as a distinct spiral galaxy will cease to exist. The combined galaxy will likely be an elliptical, a football-shaped collection of stars with no spiral arms, no organised disk structure, just a vast swarm of stars orbiting in random directions around a common centre. But even that won't be the end. Galaxies can persist for trillions of years. Long after our Sun has died, long after Earth is gone, the stars in the Milky Way Andromeda merger will continue orbiting, continue shining, continue the slow process of stellar evolution. New stars will form from the remaining gas until all the gas is used up or expelled. Eventually, in the far future, trillions of years from now, the galaxy will consist only of stellar remnants, white dwarfs, neutron stars, and black holes slowly cooling in the darkness as the universe expands and cools around them. The Milky Way has a history that extends billions of years into the past and will extend billions or trillions of years into the future. Our existence, human existence, occupies an infinitesimally small sliver of that timeline. We evolved within the last few million years on a planet that formed 4.6 billion years ago, orbiting a star that's about the same age, in a galaxy that's nearly 3 times older than our Sun. We are latecomers to this story, recent arrivals in a narrative that began long before anything remotely like us existed, and will continue long after we're gone. And yet we're here now, in this moment, able to look up and see the galaxy we're part of, able to piece together its history from starlight and mathematics, able to understand our place in this vast cosmic timeline. That understanding doesn't make us less insignificant, but it does make our insignificance meaningful somehow. A conscious awareness of scale and time that gives our brief existence a kind of poignant beauty, like a mayfly understanding that its single day of life is part of a pattern that extends far beyond any individual insect's experience. Our Sun orbits the galactic centre at approximately 250 kilometers per second, completing one full orbit every 230 million years. This period, called a galactic year or cosmic year, provides a fascinating way to think about Earth's history and the timescales involved in galactic processes. Since our Sun formed 4.6 billion years ago, it has completed approximately 20 orbits around the galaxy, 20 times around the centre, 20 cosmic years. Each orbit took it through different regions of the galactic disk, different spiral arms, different stellar neighbourhoods. The Sun we see today has travelled billions upon billions of kilometres through space, carrying Earth and the other planets with it, tracing a path through the galaxy that spirals inward and outward slightly as we orbit, creating a complex three-dimensional trajectory through space and time. Let's think about what one galactic year means in terms of Earth's history. 230 million years ago, our solar system was last at approximately this position in its galactic orbit. That was the early Triassic period on Earth. The Permian extinction, the worst mass extinction in Earth's history, had just ended. Life was recovering, slowly repopulating the devastated ecosystems. Dinosaurs hadn't evolved yet. They wouldn't appear for another few tens of millions of years. Mammals didn't exist. Flowering plants didn't exist. The world looked entirely alien. One galactic year ago, Earth was a very different place. And yet, cosmically speaking, we were right here, in this same general region of the galaxy, passing through the same spiral arm we're passing through now. The stars around us were different. Some stars that were neighbours then have drifted away. New stars have drifted into our neighbourhood. But the large-scale structure, the spiral arm, the distance from the galactic centre, all of that is similar, going back 2 galactic years, 460 million years ago. We reached the Ordovician period. Life existed only in the oceans. No plants or animals had colonised land yet. The Earth was blue and brown and barren on its continents, with all the complexity of life concentrated in shallow seas where trilobites crawled and early fish swam. 2 orbits ago, and Earth was unrecognizable. 3 galactic years takes us back to the Precambrian, before complex life, before the Cambrian explosion. To an era when the most complex organisms were simple multicellular creatures and bacterial mats. 4 galactic years ago, Earth was still in its youth, perhaps just developing its first stable continents, still being bombarded occasionally by large asteroids left over from the solar system's formation. And if we go all the way back to the beginning, to the Sun's formation, we can imagine our solar system starting its first galactic orbit, freshly formed from a collapsing molecular cloud, surrounded by a disk of debris that would eventually coalesce into planets. That first orbit saw the formation of Earth, the formation of the Moon from a giant impact, the late heavy bombardment, the emergence of the first life. All of that happened during the Sun's first trip around the galaxy. Each orbit has taken roughly 230 million years, long enough for entire eras of Earth's history to unfold, long enough for continents to drift thousands of kilometres, for mountains to rise and erode away, for new species to evolve and dominate and go extinct. The galactic year provides a natural timescale for thinking about these slow changes, a cosmic clock ticking away the ages, and we're currently partway through our 21st orbit. Sometime in the next few 100 million years we'll complete it and begin our 22nd. By then, Earth's continents will have moved significantly. They might be forming a new supercontinent. The climate will be different. The sun will be slightly brighter, slightly hotter, as it gradually increases in luminosity over its main sequence lifetime. Life will have evolved in directions we can't predict. Human civilization, if it still exists in any form, will be unrecognizably different. But the galaxy will look much the same. The spiral arms will still be there, still populated by roughly the same number of stars. Our neighbourhood will have changed slightly as stars drift in their individual orbits. But the large-scale structure will persist. The Milky Way operates on timescales that dwarf even the 100-million-year cycles of Earth's geological history. A galactic orbit is a long time for us, for any biological organism, for any planetary ecosystem. But for the galaxy, it's just the ticking of a clock, one of billions of orbits happening simultaneously as hundreds of billions of stars trace their paths through the galactic disk. All of us moving together yet separately, individuals in a vast collective dance that's been ongoing for 13 billion years and will continue for billions more. In approximately 4 to 5 billion years, the Milky Way and Andromeda galaxies will collide. This isn't speculation or distant possibility. The galaxies are already approaching each other at about 110 kilometers per second. Astronomers can measure Andromeda's motion through careful observations of its position and spectral lines, and the mathematics is clear. Collision is inevitable. It's one of the few things we can predict with certainty about the far future. Andromeda, also called M31, is the nearest large galaxy to the Milky Way, about 2.5 million light-years away. It's slightly larger than our galaxy, containing roughly 1 trillion stars compared to our few hundred billion. It's a spiral galaxy like ours, with its own beautiful structure, its own stellar populations, its own history of formation and merger. From Earth, it's visible to the naked eye as a faint smudge in the constellation Andromeda, though what you're seeing is just the bright central core. The full extent of Andromeda's disk is actually several times larger than the full moon in our sky. We just can't see most of it because it's too dim. The collision, when it happens, will be a slow-motion catastrophe, though catastrophe might be the wrong word since the individual stars will almost certainly not collide. Space is so empty that even when 2 galaxies merge, stellar collisions are extraordinarily rare. The stars will simply pass by each other, their orbits perturbed by the combined gravitational field of both galaxies, creating new, more chaotic trajectories. But the gas clouds will collide, and that collision will be spectacular. When the cold molecular clouds from both galaxies crash into each other, They'll compress, heat up, and trigger enormous bursts of star formation. The merged galaxy will experience a starburst phase, creating millions of new stars in a relatively short time, perhaps a few 100 million years. The night sky from any surviving planet in either galaxy will be incredibly bright during this period, filled with brilliant young stars and the glowing nebulae where they're being born. The supermassive black holes at the centres of both galaxies will eventually spiral together and merge, releasing gravitational waves so powerful they'll be detectable halfway across the universe. This merger will create a single, larger, supermassive black hole containing the combined mass of both progenitors, roughly 10 million solar masses, sitting at the centre of the new combined galaxy. The final product of this merger will likely be an elliptical galaxy, a football-shaped collection of stars with no spiral structure, no organised disk, no neat division into a central bulge and spiral arms, just stars, orbiting in all directions, their paths randomised by the chaotic gravitational interactions of the merger. Astronomers have already named this future galaxy Milkomeda, a portmanteau of Milky Way and Andromeda. What will this mean for Earth, if Earth still exists? Our Sun will be about 9 billion years old, 90 minutes. You've been here for 90 minutes, quietly, patiently, choosing this over everything else the world was offering you tonight. Do you know how rare that is? Most people cannot sit with something slow and meaningful for more than a few minutes before reaching for something louder. But not you. Not tonight. This channel exists for exactly this kind of person, and a like and subscribe is how we find more of them. It is how we find each other. Thank you for still being here. Now let's continue. Our Sun will be about 9 billion years old by the time the collision happens, nearing the end of its main sequence life. It might have already begun expanding into a red giant, possibly engulfing Mercury and Venus, possibly even Earth. If Earth survives as a planet, it will be a dead world, heated beyond habitability by the aging Sun, its oceans long since evaporated, its atmosphere blown away. But even if Earth and humanity are long gone, the solar system will endure. The Sun and its remaining planets will survive the merger. Flung on to some new orbit within Milkomeda, we might end up closer to the galactic centre. We might be flung toward the outskirts. Computer simulations suggest there's even a small chance our solar system could be ejected from the merged galaxy entirely, becoming a lonely stellar system drifting through intergalactic space. The collision will take several billion years to complete. The galaxies will approach, pass through each other, separate slightly as their mutual gravity pulls them back together, pass through each other again, gradually losing energy to dynamical friction until they settle into a single merged system. During this process, the night sky from any planets in either galaxy will be extraordinary, filled with tidal streams of stars, bright regions of intense star formation, two galactic cores visible simultaneously, slowly spiralling together. This is the fate awaiting the Milky Way, not eternal existence as a pristine spiral, but merger, transformation, death of the current structure and birth of something new. It's a reminder that even galaxies aren't permanent. Even these vast structures change and evolve and end. The Milky Way we see today, that we're trying to understand our place within, is a temporary configuration, one moment in a much longer story that will eventually involve merger and transformation into something completely different. And perhaps that's okay. Perhaps change, even on these vast scales, is just part of what existence means in a universe governed by gravity and time. Let's go further into the future now, much further, to time scales that stretch the imagination even more than the spatial scales we've been contemplating. Let's think about what happens to the Milky Way, or Milkomeda, or whatever structure our galaxy becomes, over trillions of years. Stars form from gas and dust. They live, fusing hydrogen into helium and heavier elements, and then they die, some gently puffing off their outer layers as planetary nebulae, others exploding violently as supernovae. But in either case, they return material to the interstellar medium, and that material can be used to form new stars. This cycle has been ongoing for billions of years, with each generation of stars recycling the material from previous generations. But the cycle can't continue forever. With each generation, more and more gas gets locked up in stellar remnants that don't return it to the interstellar medium. White dwarfs, the slowly cooling cores of sun-like stars, hang on to their mass essentially forever. Neutron stars and black holes, the remnants of massive stars, likewise permanently remove mass from the star formation cycle, and some gas gets expelled from the galaxy entirely by stellar winds and supernova explosions, lost to intergalactic space. Over time, the gas available for new star formation decreases, the star formation rate declines, fewer and fewer new stars are born. Current models suggest that the Milky Way's star formation has already peaked and is now slowly declining. In a few billion years, after the merger with Andromeda, there will be a temporary spike in star formation from the collision of gas clouds, but after that, the decline will resume. In about 1 trillion years, give or take a few hundred billion years, the last stars will form in what was once the Milky Way. After that, no more star formation. The galaxy will consist only of stars that already exist, and the remnants of stars that have already died. For a while, perhaps several trillion years, the galaxy will still look somewhat normal, at least to a distant observer. There will be stars, mainly dim red dwarfs, the longest-lived stellar type, still burning their hydrogen fuel slowly and steadily. But eventually even the red dwarfs will run out of fuel. They'll cool and fade, becoming dim brown dwarfs and eventually cold black dwarfs, objects that emit essentially no light. White dwarfs, the remnants of sun-like stars, will also cool over trillions of years, radiating away their thermal energy until they too become cold and dark. By about 10 trillion to 100 trillion years from now, the galaxy will contain almost no shining stars, just remnants. White dwarfs and brown dwarfs and neutron stars and black holes, all slowly cooling in the darkness. This is called the degenerate era by cosmologists. It's the period when the universe will consist primarily of stellar remnants rather than active stars. It will last far longer than the current stelliferous era, the age of stars, has lasted. Trillions upon trillions of years of darkness, with only occasional flickers of light when objects collide, or when brown dwarfs momentarily flare from gravitational contraction. Eventually even the stellar remnants begin to decay. White dwarfs might crystallize, their carbon and oxygen atoms forming vast cosmic diamonds floating in space. Protons might decay, though this is theoretical and has never been observed. If protons do decay, then even the white dwarfs and neutron stars will slowly evaporate over timescales of 10 to the 34 years or more, unimaginable stretches of time when the universe is mostly empty and cold. Black holes will be among the last objects to vanish. Through a process called Hawking radiation, black holes slowly evaporate, emitting particles and losing mass. For stellar mass black holes, this process takes about 10 to the 67 years. For supermassive black holes like the one at the Milky Way's centre, it takes even longer, perhaps 10 to the 100 years. But eventually even they will evaporate, flashing briefly brighter as they expire in their final moments, leaving behind nothing but a faint bath of radiation dispersing into the infinite expansion of space. This is the heat death of the galaxy and eventually the universe. Not a dramatic explosion or catastrophic collapse, but a slow, inevitable cooling and dispersal, everything spreading thinner and thinner, colder and colder, until there's nothing left that could meaningfully be called a structure, just a faint haze of particles and radiation expanding forever into the void. These timescales are so vast that human minds can't really grasp them. 10 trillion years, 10 to the 67 years, 10 to the 100 years. For comparison, the current age of the universe, 13.8 billion years, is a rounding error, a brief flicker at the very beginning of cosmic history. If the universe's timeline were compressed to a single year, We're currently living in the first second of January 1st. The age of stars will last until perhaps March or April. The degenerate era will occupy the rest of the year and extend thousands or millions of years beyond. And yet, here we are, in the brief, bright, beautiful moment when stars shine, when galaxies sparkle with hundreds of billions of points of light, when planets orbit those stars and life can evolve and intelligence can emerge and wonder about all this. We exist in the golden age of the universe, the cosmologically brief period when the cosmos is young and energetic and full of light. It won't last, but it's happening now, and we're here to witness it, to understand it, to feel both our insignificance in scale and our extraordinary luck in timing. There's something we should pause to appreciate, something we might take for granted. We can see the Milky Way, not just through telescopes, though those certainly help. We can see it with our naked eyes, arcing across the night sky like a river of light, that dense band of stars visible on dark, clear nights far from city lights. This is a privilege not guaranteed to all times or all places. If we lived near the galactic centre, the night sky would be too bright, too full of stars. For the Milky Way band to stand out as a distinct feature, everything would be stars, bright and numerous, with no clear sense of structure. If we lived in the sparse regions between spiral arms or far out at the galactic edge, the Milky Way band would be dimmer, less impressive, a faint glow easily washed out by moonlight or atmospheric haze. But we live 2/3 of the way out, in the galactic suburbs, where the stellar density is high enough to create a beautiful view, but low enough that we can still see individual stars clearly. We can see the Milky Way as structure, as something distinct from the general star field, as a feature of our night sky that inspired our ancestors to tell stories and create myths long before we understood what we were looking at. And we live in an era when the Milky Way is visible at all. In the far future, after the merger with Andromeda, the structure will be different. The spiral arms will be gone. The edge-on view of the galactic disk, that characteristic band across the sky, will be replaced by a more uniform distribution of stars in an elliptical galaxy. The Milky Way, as a visual phenomenon, will cease to exist. Going further into the future, to the degenerate era, there won't be enough light for anything to see. Stars will have burned out. The galaxy will be dark. Even if intelligent beings somehow existed in that far future, perhaps as digital entities powered by the dying heat of cooling white dwarfs, they wouldn't be able to see the galaxy around them. There would be nothing to see. Just darkness, punctuated by the occasional dim glow of a cooling remnant. We also live in a time when the universe is still young enough, still small enough, that we can see other galaxies. The universe is expanding, and that expansion is accelerating. Distant galaxies are moving away from us faster and faster. Eventually, in hundreds of billions of years, the expansion will have carried everything beyond our observable horizon. Future astronomers, if they exist, will live in a universe where the Milky Way, or Milkomeda, or whatever it's become, appears to be the only galaxy, surrounded by empty space, with no other galaxies visible anywhere. They won't have access to the evidence we have for the Big Bang, for the expansion of the universe, for the cosmic microwave background radiation. Much of modern cosmology will be impossible for them, because the relevant evidence will have expanded beyond their ability to observe it. They'll live in a lonelier, more mysterious universe than we do, with fewer clues about cosmic history available to them. We, right now, in this era, have the privilege of living when the universe is old enough for complex structures to have formed, for stars and galaxies and planets and life to exist, but young enough that we can still see the grand cosmic structure, can still observe other galaxies, can still detect the faint echo of the Big Bang in the cosmic microwave background. We live in the perfect era for astronomy, for cosmology, for understanding our place in the universe. And we have the privilege of being conscious observers, beings who can look up, wonder, question, and eventually understand. The vast majority of the universe's matter is unconscious. Stars don't know they're stars. Black holes don't contemplate their own existence. Dark matter, whatever it is, doesn't wonder about its nature. But we do. We've evolved the capacity to ask where we are, how big everything is, what it all means. This capacity arose on a small planet in an unremarkable solar system, in the suburbs of a large spiral galaxy, at a time in cosmic history when the universe is bright and structured and knowable. All of these factors had to align for us to exist, for us to be able to see what we see, for us to develop the science and mathematics needed to understand our cosmic address. In a very real sense, we are the universe becoming aware of itself. We're made of atoms forged in stars, arranged through billions of years of evolution into patterns complex enough to contemplate the very stars that created us. We're cosmically insignificant in scale, yes, but we're also cosmically unique in our awareness, our curiosity, our drive to understand. That's worth something. That matters, even if it doesn't make us larger or more central or more important in any physical sense. The Milky Way doesn't care that we exist. It doesn't notice us. It will continue regardless of whether we're here or not. But we notice it. We see it. We map it. We understand it. And in doing so, we create meaning where none existed before. We add consciousness to a universe that's mostly unconscious. We light a small candle of awareness in the cosmic dark. Perhaps that's enough. Perhaps that's what significance looks like when you're very, very small. Not being large, not being central, but being aware, being curious, being willing to confront your own insignificance and find beauty in it, rather than despair. Let's bring this back to you now, to the body you're resting in as you listen to this. Every atom in your body has a story, a cosmic origin that connects you directly to the Milky Way, to the processes we've been discussing, to the deaths of stars that happened billions of years ago. The hydrogen in your body, the single protons that make up about 10% of your atoms, formed in the Big Bang itself, in the first few minutes after the universe began. These are primordial atoms, older than any star, older than any galaxy. They've been cycling through the universe for nearly 14 billion years, possibly part of earlier stars, possibly drifting through interstellar space for eons, eventually incorporated into the molecular cloud that formed our solar system, and then into Earth, and then into you. But most of your body is heavier elements: carbon, nitrogen, oxygen, phosphorus, calcium, iron. These weren't made in the Big Bang. They couldn't have been. The early universe was too hot, too energetic for complex nuclei to form. These elements were forged later, inside stars, through nuclear fusion. The carbon in your cells, the structural foundation of organic chemistry, was made through the triple alpha process inside red giant stars. 3 helium nuclei fused together to make carbon, releasing energy and allowing the star to continue shining even after it's exhausted its hydrogen fuel. When these red giants eventually died, gently puffing off their outer layers as planetary nebulae, they scattered their newly created carbon into space. The oxygen you're breathing right now was also made in stars, through fusion processes that combine helium and carbon. Every breath contains atoms created in stellar cores, expelled into space through stellar winds or supernova explosions, incorporated into new generations of stars and planets, and eventually into you. The calcium in your bones required more extreme conditions. It formed in massive stars near the end of their lives, when core temperatures reached hundreds of millions of degrees, and fusion created progressively heavier elements. These stars died as supernovae, violent explosions that briefly outshone entire galaxies, scattering their newly forged heavy elements across light years of space. The iron in your blood, essential for carrying oxygen through your body, was also made in supernova explosions. Iron represents the endpoint of energy-producing fusion. You can't extract energy by fusing iron into heavier elements. So iron accumulates in the cores of massive stars until the core becomes unstable and collapses, triggering the supernova that distributes the iron throughout the galaxy. Even heavier elements, like the iodine in your thyroid or the trace amounts of gold and platinum in your body, required even more extreme conditions. They were probably made during neutron star collisions. Extraordinarily violent events where two dead stellar cores spiral together and merge, creating brief conditions hot and dense enough to forge elements heavier than iron. So the atoms in your body come from different sources, different types of stellar deaths, different events scattered across the Milky Way's history. Some of your atoms might have come from stars that died 10 billion years ago. Others might have come from stars that died more recently, just a few billion years ago. They travelled through space as part of the interstellar medium, mixed with gas and dust in molecular clouds, and eventually found themselves in the region that would become our solar system. 4.6 billion years ago, a molecular cloud collapsed, possibly triggered by the shockwave from a nearby supernova. That collapse formed our sun and the disk of material around it that would become the planets. Earth formed from the rocky material in the inner solar system, accumulating the heavy elements that earlier generations of stars had created. Your atoms were there, incorporated into the early Earth, cycled through geological processes, eventually becoming part of the biosphere, passing through countless organisms over billions of years before ending up in you. You're not separate from the Milky Way. You're made of it. You're a temporary arrangement of galactic matter, atoms that have cycled through the galaxy for billions of years, briefly organised into the pattern we call a human being, eventually to be returned to Earth and, on much longer timescales, back to the galaxy itself when the sun dies and disperses its remaining material into space. This connection is not metaphorical. It's literal, physical, verifiable through spectroscopy and nuclear physics. The Milky Way created you, not intentionally, not with any purpose, but through the blind processes of stellar evolution and planetary formation and biological evolution. You're stardust, and when you look up at the Milky Way in the night sky, you're looking at the place your atoms came from, the cosmic home that built you from the ashes of dead stars. That's a connection that transcends significance or insignificance. It's simply what you are, a piece of the galaxy that became conscious enough to know it's a piece of the galaxy. There's a philosophical principle worth considering as we contemplate our cosmic insignificance. The Anthropic Principle, particularly the weak Anthropic Principle, which notes that we can only observe the universe from locations and times where conscious observers can exist. This sounds tautological, and in some sense it is, but it has interesting implications for how we think about our place in the cosmos. We find ourselves on Earth, a planet in the habitable zone of a stable star, in a galaxy that's old enough for heavy elements to be abundant but young enough that stars still shine. We find ourselves in a universe where the fundamental constants of physics allow for complex chemistry, stellar fusion, and the slow processes of planetary formation and biological evolution. We find ourselves here, now, conscious and curious. But we couldn't find ourselves anywhere else. If we lived near the galactic centre, the radiation environment would likely be hostile to life. If we lived in a region with no heavy elements, no rocky planets could form. If we lived in the far future during the degenerate era, there would be no energy sources to power biology. If we lived in a universe where the fundamental constants were slightly different, stars might not form, or they might burn out too quickly, or chemistry might not work the way it does. The fact that we exist means we must find ourselves in a location and time where our existence is possible. We're biased observers, capable of observing only those portions of space and time compatible with our existence. We can't observe regions or eras incompatible with consciousness, because in those regions and eras, there's no one to do the observing. This doesn't make us special in any cosmic sense. It doesn't mean the universe was designed for us, or that we're the purpose of creation. It simply means that the subset of the universe we can observe is by necessity the subset compatible with our existence. We're selection biased toward habitable conditions because uninhabitable conditions don't produce observers. Think about it this way. The Milky Way probably contains billions or even trillions of planets. Most of them are likely uninhabitable. Too hot, too cold, no atmosphere, wrong chemistry, unstable orbit, too much radiation, any number of factors that make them unsuitable for life as we know it. But we don't find ourselves on those planets. We find ourselves on one of the rare planets where conditions permit complex chemistry and biological evolution. Not because we're special, but because we couldn't exist anywhere else. This applies to time as well. We exist roughly 14 billion years after the Big Bang, in an era when second or third generation stars have enriched the interstellar medium with heavy elements, when the universe has cooled enough for stable structures to form, when there's still enough energy density for stars to shine, but not so much that everything's too chaotic for planetary systems to persist. We couldn't exist in the first billion years of the universe. We probably can't exist trillions of years in the future. We're constrained to this relatively narrow temporal window when conditions permit our kind of complexity. Understanding this selection effect helps contextualize our cosmic insignificance. Yes, we're tiny. Yes, we're brief. Yes, we're confined to one small planet in a vast galaxy in an even vaster universe, but we're not surprising given the selection effect. Conscious observers, wherever they arise, will always find themselves in locations and times that permit consciousness. They'll always be small compared to the cosmic structures around them. They'll always be temporary compared to the lifespan of stars and galaxies. The question isn't quote 3, but rather quote 4, and the answer might be that insignificance is the necessary condition for significance. Only in a universe large enough and old enough and complex enough to contain billions of galaxies with billions of stars each can the intricate processes of planet formation and biological evolution have enough room and time to produce observers. We're insignificant because we're in a universe where significance requires insignificance, where conscious observers can only arise in contexts so vast that the observers themselves are vanishingly small by comparison. Our smallness isn't a bug in the cosmic design. It's a feature, a necessary condition for our existence. And recognizing that doesn't make us larger or more central, but it does make our existence less paradoxical, less surprising, less a puzzle that needs solving, and more simply what observers should expect to find when they become aware enough to ask where they are. We've focused a lot on Earth's insignificance, on how small we are within the Milky Way, but it's worth considering that we're probably not alone in our smallness. The galaxy likely contains billions of other planets, and many of them might harbour life, might have their own pale blue dot moments, might be home to beings who look up at their night sky and wonder about their place in the cosmos just as we do. The discovery of exoplanets, planets orbiting other stars, has exploded in recent decades. We've found thousands of them using various detection methods, watching for the slight dimming of stars as planets pass in front, measuring the wobbles in stellar positions caused by orbiting planets, even directly imaging some planets around nearby stars. The data suggest that planets are common, that most stars probably have them, that the Milky Way might contain hundreds of billions of planets. Among those hundreds of billions, how many might be habitable? How many might be in the right temperature range, with the right chemistry, with the right atmospheric conditions to support liquid water and complex organic molecules? Conservative estimates suggest there might be billions of potentially habitable planets in our galaxy alone. Billions of worlds where life could potentially arise. We don't know if life has actually arisen on any of these worlds. The origin of life is still poorly understood. We don't know if it's common or extraordinarily rare, if it arises naturally given the right conditions, or if Earth represents an unlikely fluke, a statistical anomaly in an otherwise lifeless galaxy. But the sheer number of potentially habitable planets makes it seem unlikely that Earth is unique. And if life has arisen elsewhere, Has it developed complexity? Has it evolved intelligence? Has it built civilizations? These questions multiply the uncertainty. Life might be common, but intelligence rare. Or intelligence might be common, but technological civilization fleeting. Or technological civilizations might be common, but separated by such vast distances that they never detect each other. This last possibility is particularly poignant given what we've discussed about galactic scale. If there are other civilizations out there, other technological species looking up at their night sky with radio telescopes and optical observatories, trying to detect signs of other life, they face the same isolation we do. Radio signals travel at the speed of light. A signal from a civilization 50,000 light years away would take 50,000 years to reach us. If they sent a signal today, it wouldn't arrive until long after our civilization has likely transformed beyond recognition, or possibly ceased to exist. And even if we received such a signal, our reply would take another 50,000 years to reach them. The conversation, if you can call it that, would be measured in time periods longer than recorded human history. It's hard to imagine maintaining any kind of meaningful dialogue over such timescales. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of active, communicative civilizations in the Milky Way. It multiplies together various factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per star system, the fraction where life actually arises, the fraction where intelligence evolves, the fraction where technological civilization develops, and the length of time such civilizations release detectable signals into space. Depending on the values you plug into these factors, you can get answers ranging from quote 5, quote to quote 6, quote, we don't know which is correct. We don't have good data for most of these factors. We have exactly one example of life, intelligence, and technological civilization. Us. Drawing statistical conclusions from a sample size of 1 is essentially impossible. But let's assume, for the sake of contemplation, that we're not alone. Let's assume there are other civilizations out there, scattered across the Milky Way, each of them on their own pale blue dot, each of them cosmically insignificant. Each of them wondering if they're alone. The galaxy would be full of isolated intelligences, islands of consciousness in an ocean of stars, each one able to detect the other's stars but unable to visit, unable to communicate meaningfully, condemned to a kind of cosmic loneliness despite being surrounded by neighbours. This scenario is both comforting and melancholy. Comforting because it means we're not unique, not the only consciousness in the universe, not bearing the sole burden of being the universe's only self-aware component. But melancholy because it means the distances that make us insignificant also make us unreachable, that the same scale that humbles us also isolates us, that we might share the galaxy with countless other civilizations, and yet remain forever alone, never touching, never truly connecting across the light years. Or perhaps we're alone. Perhaps life is rare, intelligence rarer still, and we're the only technological civilization in the Milky Way, possibly in the entire observable universe. That possibility carries its own weight, its own form of significance, even within insignificance. If we're alone, then we're the only part of the galaxy capable of knowing the galaxy exists, the only consciousness in a vast unconscious cosmos, a single candle of awareness in an otherwise dark universe. Either way, alone or not, we're cosmically small. Either we're one tiny consciousness among many, all of us small together, or we're the only consciousness, singular and precious and utterly dwarfed by the unconscious matter surrounding us. The scale remains overwhelming, the insignificance remains real. But the possibility of others, or the responsibility of being alone, adds texture to that insignificance, makes it meaningful in ways that pure physics can't capture. We've spent this entire journey establishing how small Earth is, how insignificant we are within the Milky Way, how vast the scales of space and time are compared to our brief existence on one tiny planet. But now, as we approach the end of this exploration, it's worth asking, what does insignificance actually mean? Does being small make us meaningless? Does being brief make us pointless? The easy answer, the nihilistic answer, would be yes. We're specks of dust in a vast cosmos that doesn't care if we exist. Nothing we do matters on cosmic scales. The sun will die regardless of our achievements or failures. The Milky Way will merge with Andromeda, whether we're here or not. The universe will expand and cool toward heat death completely indifferent to anything humans have ever done or will ever do. But that answer, while technically true, misses something important. It confuses physical scale with value, size with significance, duration with meaning. These are not the same thing. A moment can be brief and still matter. A place can be small and still be home. An existence can be finite and still contain joy, love, curiosity, beauty, all the things that make life worth living. Consider, a human lifetime is roughly 70 or 80 years. That's infinitesimal compared to the age of the universe, compared to the lifetime of stars, compared to the timescales of galactic evolution. But within that brief span, so much happens. You experience consciousness, awareness, the sensation of existing. You form relationships, create memories, learn, grow, change. You suffer and celebrate. You wonder about your place in the cosmos. None of this registers on cosmic scales. The universe doesn't track individual human experiences. But that doesn't make the experiences less real to you, less meaningful in the context of your own life. Meaning isn't something the universe grants. It's something conscious beings create through their awareness, their connections, their understanding. The Milky Way is vast and old and will endure long after we're gone. But it's also unconscious. It doesn't know it exists. It doesn't wonder about itself. It doesn't contemplate its own structure or understand its place in the larger universe. We do. We're small and brief, yes, but we're also aware in ways the galaxy is not. We represent something the galaxy alone cannot produce: consciousness, understanding, the capacity to know and wonder. In a very real sense, we give the universe meaning. Without conscious observers, the cosmos would simply exist, following the laws of physics, structures forming and dissolving, stars being born and dying, galaxies merging and evolving, all of it happening in a kind of blind mechanical fashion, with no one to witness, no one to understand, no one to care. But we witness. We understand, at least partially. We care. We look up at the night sky and feel awe. We build telescopes to see farther. We develop mathematics to comprehend the scales. We create art inspired by cosmic beauty. We write poetry about our place among the stars. We tell stories, we ask questions, we seek meaning even in the face of overwhelming vastness. This is significant not despite our smallness, but because of it. The fact that tiny, brief, fragile beings on one small planet can comprehend the galaxy they're part of, can measure cosmic distances, can understand stellar evolution, can map the Milky Way structure from the inside, this is remarkable. We're the universe becoming self-aware, matter complex enough to contemplate its own existence. Insignificance in scale doesn't equal insignificance in meaning. A single human life contains more meaning, more experience, more consciousness than an entire galaxy of unconscious matter. The galaxy is larger, yes. It will endure longer, yes. But it doesn't feel, doesn't think, doesn't know, and that makes all the difference. The question isn't whether we're cosmically significant. Clearly we're not. We're tiny and temporary and confined to one small world. The question is whether cosmic significance is the only kind that matters, and the answer might be no. Local significance, personal significance, the significance we create through consciousness and connection and understanding might be the only significance there is. The Milky Way is beautiful and vast and worthy of awe. Understanding our smallness within it is important for perspective, for humility, for comprehending our actual place in the cosmos. But that understanding doesn't have to lead to despair or nihilism. It can lead instead to wonder, to appreciation for the privilege of existing during this brief cosmic moment when stars shine and planets harbour life and consciousness arises to contemplate it all. We're insignificant, yes, and that's okay. That's not a tragedy. It's simply what we are. Small, temporary, local, and yet somehow capable of understanding our own smallness, finding beauty in it, creating meaning despite it. Up at the Milky Way and feel connected to up at the Milky Way and feel connected to something larger than ourselves, even as we understand just how large that something is and how small we are by comparison. After all this contemplation of scale, after understanding just how tiny Earth is within the Milky Way, after grappling with our cosmic insignificance, let's return to where we started. Home, this small planet, this pale blue dot, this unremarkable world orbiting an average star in the suburbs of a large spiral galaxy. Earth is home not because it's cosmically important, but because it's where we are, where we've always been, where everything we've ever known has happened. Every person you've ever met lives here. Every place you've visited is on this planet's surface. Every story, every achievement, every failure, every moment of joy or sorrow in human history occurred right here, on this small world. Carl Sagan, in his meditation on the pale blue dot photograph, made this point beautifully. He noted that Earth is the only home we've ever known, the only place where life is known to exist, the only world that's ours. He observed that there's nowhere else, at least in the near future, that we can migrate to. Like it or not, for the moment, Earth is where we make our stand. The smallness of Earth should inspire care, not despair. We share this one world. All of us, all 7 or 8 billion humans, along with millions of other species, share this tiny planet floating through space. We can't escape to another world if we ruin this one. There's no backup Earth waiting in some other star system we can reach. Understanding cosmic scale puts human conflicts in perspective. The borders we fight over, the territories we claim, the nations we divide ourselves into, all of these are human constructs drawn on the surface of a planet, so small it's barely visible from the outer edge of our own solar system. From the Milky Way's perspective, from any perspective beyond our immediate orbital neighbourhood, all human divisions are invisible, meaningless, artifacts of psychology rather than cosmic reality. We're all on this small world together. We're all, in the most literal sense, Earthlings, children of this planet, sharing its surface and its resources and its fate. The cosmic perspective doesn't erase human concerns or make our daily lives less important, but it does provide context. It reminds us that we're part of something larger, that we share a common origin and a common home, that whatever divides us is smaller than what unites us. Earth is also, as far as we know, extraordinarily rare. We've found thousands of exoplanets, but we haven't found another Earth yet, another world with liquid water, a protective atmosphere, a stable climate, and abundant life. Earth might not be unique, but it's certainly uncommon, a rare jewel in the galactic darkness, a world where conditions aligned perfectly for life to flourish. The biosphere, that thin shell of life surrounding our planet, is precious precisely because it's fragile and possibly rare. Life has persisted on Earth for billions of years, surviving mass extinctions and environmental changes, adapting and evolving and filling every available niche. The diversity of life here, from bacteria to blue whales, from mosses to sequoias, from coral reefs to Arctic tundra, represents billions of years of evolutionary experimentation, a complexity that might be uncommon in the galaxy. We're part of that biosphere, products of the same evolutionary processes that created every other living thing on Earth. We're related literally to every organism that's ever lived here, sharing common ancestry going back billions of years to the first simple cells. We're not separate from Earth's life. We're embedded in it, dependent on it, made of the same stuff, operating by the same biochemical principles. Understanding our cosmic insignificance should make us more protective of Earth, not less. If we're tiny and brief and confined to one small world, then that world matters enormously, not cosmically, but to us, to our continued existence, to the flourishing of life and consciousness on the one planet where we know it exists. Home is where you are. For us, that's Earth. A small world, yes. An insignificant speck in the Milky Way, yes. But also the most beautiful, most complex, most alive place we've ever seen. The only place we've ever known. The only place for now and probably for a very long time to come where humans can live and thrive. The cosmic perspective teaches us humility, shows us our true scale, reminds us that we're not the centre of anything, but it also teaches us appreciation for the one place where we exist, the one world that supports us, the one pale blue dot that's ours to care for, to protect, to call home despite its cosmic insignificance, or perhaps because of it. We're small, yes, but this small place is everything to us, and that makes it significant in the only way that ultimately matters. It's where we are, where we've always been, where we belong in this vast, largely empty, profoundly beautiful galaxy we're still learning to understand. Before I say goodnight, I need you to know something. When this video was posted, most people scrolled right past it. They saw the length, they saw the topic, and they kept scrolling. But you didn't. You stayed for 2.5 hours, you chose depth over speed, and wonder over noise, and I think that says something beautiful about the kind of person you are. If this channel has given you something tonight, a little more peace, a little more wonder, a little more understanding of the world you live in, then a like and subscribe is the kindest thing you can leave behind before you sleep. Not just for this channel, but for the next person out there tonight who needs exactly what you just found here. Now, rest. You have earned it. From the pale blue dot. We've travelled together tonight, you and I. We started here on Earth, and we pulled back step by step, layer by layer, revealing the scale of our cosmic home. We moved from our solar system to our stellar neighbourhood, from our spiral arm to the galactic centre, from the disk to the halo, from the present to the distant past and far future. We measured light years and galactic years. We contemplated dark matter and stellar nurseries, rogue planets and galactic cannibalism, the birth of stars and their inevitable deaths. Along the way, we confronted an uncomfortable truth. We're cosmically insignificant. Earth is tiny. Our solar system is unremarkable. Our position in the Milky Way is utterly ordinary. We exist for a brief moment in cosmic history, a flash of consciousness in a universe that's mostly unconscious and will endure far longer than we ever will. The scale is overwhelming. The vastness is undeniable. And yet, I hope you found something other than despair in this journey. Because here's what I think about insignificance, about smallness, about our brief existence on one pale blue dot in a galaxy containing hundreds of billions of others. It's not the tragedy we sometimes make it out to be. Being small doesn't mean being meaningless. Being temporary doesn't mean being pointless. The universe might not care about us, but we care. We create meaning through our awareness, our connections, our capacity to understand and wonder and feel. You're made of stardust, literally. Atoms forged in stellar cores and scattered across the galaxy, eventually finding their way to Earth and into you. You're a temporary arrangement of cosmic matter, briefly aware, briefly capable of contemplating the vast structure you're part of. That's not nothing. That's extraordinary, actually. Perhaps the most extraordinary thing in the universe. Matter becoming conscious enough to know it's matter. Wherever you are in the world right now, wherever you've been listening from, I hope you're comfortable. I hope your breathing has slowed and deepened. I hope your thoughts have quieted, or if not quieted, at least shifted to contemplation rather than worry. I hope your body feels heavy and warm and ready for sleep. Look up at the Milky Way tonight if you can. If your sky's clear and dark enough, find that band of light stretching across the heavens. That's your galaxy, the spiral of stars we've been exploring, seen from the inside. Every point of light in that band is a sun, possibly with its own planets. Possibly with its own pale blue dots where life might have arisen and wondered about its place in the cosmos. All those stars, all those worlds, all that vast cosmic architecture, and somewhere in it, invisible from any distance greater than a few billion miles, is Earth. Our home, the only one we've ever known. Small, yes. Insignificant in scale, yes. But also precious, rare, beautiful, and ours. Perhaps what we've learned tonight is that significance and insignificance aren't opposites. Perhaps they're perspectives, ways of looking at the same reality. From one angle we're nothing, specks of dust in an uncaring cosmos. From another angle we're everything, the only consciousness in the galaxy as far as we know, the only beings capable of understanding the galaxy we're part of. Both perspectives are true, both matter. And perhaps the wisdom lies in holding both simultaneously, in accepting our cosmic smallness while still finding meaning in our local, human, earthly existence. In being humble about our place in the universe while still caring deeply about what happens on this one small world where we make our stand. Sleep well tonight, wherever you are. Dream, if you dream, of spiral arms and stellar nurseries, of dark matter halos and galactic collisions, of the slow cosmic dance that's been ongoing for billions of years and will continue for billions more. Dream of pale blue dots scattered throughout the galaxy, each one potentially harbouring its own stories, its own consciousness, its own journey toward understanding. And when you wake tomorrow, remember what you are, a small part of something vast, a brief moment in something eternal, a conscious observer in a mostly unconscious universe, a child of Earth, and also a child of the stars, cosmically insignificant, and yet somehow paradoxically meaningful simply because you exist, because you wonder, because you care. Good night from our pale blue dot. Good night from the Orion arm of the Milky Way galaxy. Good night from this brief bright moment in cosmic history when stars shine and life flourishes, and consciousness arises to contemplate it all. Good night.